general relativity step by step. I'm going to set up some very simple coordinate system here, x and t, for a little person here. I'm going to write in black. And at this particular point here, he's going to emit a photon, which I'm going to draw in red. And I'm carefully choosing my units so that the photon is travelling at 45 degrees. There's a nice 45-degree slope to that angle there, and it's going to get reflected by a mirror, which I'm going to draw in here. Where's my mirror? That's going to be there, and we've got this beautiful mirror here. Well, that's great, and everybody agrees that this point here is, well, this black person with black coordinates here, his notion is that this point here and this point here are the same time. They are simultaneous in his frame of reference. And we're also noting that that distance there equals this distance here, simply because the speed of light is constant whether it's going right to left or left to right. So we've got this quite nice symmetrical, very, very simple picture. Now what I'm going to do is I'm going to introduce a new coordinate system that's appropriate for a person in a spaceship who is sitting here in his spaceship. There is spaceship, and I've got speed lines coming out there. It's not accelerating. So what I'm going to do is I'm going to draw what this system looks like to him. So again, we've got the x and the y, sorry, we've got the x and the t coordinates for the black coordinate system, which is just the same here. But now what I'm going to do is I'm going to draw what he thinks his time axis looks like, and that looks something like this. And I'm going to call that t bar, simply because an object moving along, keeps on doing that. An object moving along this line here looks to this blue person here as if it's not moving. So that's these objects moving up and down these lines here are at rest for this blue person. Now he's going to do the same experiment. He's going to send out a photon, and we'll have a look at it from his point of view here. So it goes out there, and the photon travels at 45 degrees. I'm not drawing it perfectly accurately like that. Gets reflected off the mirror, which is, I'm going to write in black, which is here. There's my mirror. And the photon gets reflected, and now it's moving right to left here. So we can see straight away that the situation is a little bit different in the blue person's perspective, because when he starts to draw his space axis will go through the origin, but it will also go through this reflection point here, x bar. So the blue person judges this event here and this event here to be simultaneous, but that's not simultaneous according to the black person here, because the line of simultaneity for the black person is the black, by definition, is the black x-axis there. So this shows us straight away that the constancy of the speed of light tells us that we need to modify our notions of simultaneity. And that modification is called the Lorentz transformation, which I'll develop over the next couple of screencasts. As I keep on saying, I don't want this to be a special relativity course, so I'm going to keep it as brief as I possibly can. I want to get up to the Lorentz transformations written in matrix notation, and then I'm going to stop talking about special relativity and get back to the cool, interesting things like black holes and cosmology and gravitational radiation, gravitational waves that I want to talk about. So, right, I'm going to stop there, and I'm going to develop the Lorentz transformations over the next couple of screencasts. Stop.